Here's the solution to one of the problems about general slicing of solids to find volumes. So this is back before we were spinning everything around axes, which means that we need to draw a more detailed picture to see what our cross sections look like. We can't assume that the cross sections are always just circles. So the description is that we have this triangular shaped base like this. That's a straight line. Don't ask. That's 15, 0. That's 0, 15. And so this is the base of a solid. I will try to be artistic, not bad. And we're told that when you take cross sections, so this is what the loaf of bread looks like looking down on it, and the 3 dimension is coming up towards us. And we want to describe what one piece looks like. It says if we slice parallel to the y-axis, slicing this way. So if I slice my piece of toast out of here, like that, notice that's a vertical slice, and so that means that I'm going to be working in terms of x. So this end of this thing is x comma 0, and the top end of it is going to be x comma whatever the equation of that line is. If you take a second and work it out, the equation of that line is y equals 15 minus x. So that's what goes in the y-coordinate. So whatever you like to do to find the equation of a line, do that with those 2 points, and you'll have y equals 15 minus x. So the top of the slice has coordinates x, 15 minus x. The bottom of the slice has coordinates x, 0. And so all I need to do is think about when I pull that piece of toast out of the loaf of bread. Remember, I'm looking down on it there, but if I take it out and let it fall over on its side, then there's the bottom. That was the triangle that I just saw. And if it falls over on its side, we're told it's a semicircle. So this is what the solid piece looks like, where where this part is was the part that was sitting right there on that stick. And so that means over here there's smaller semicircles, and over here they're bigger semicircles. So depending on where the slice is taken, I will have a different size semicircle. So what I need to do to finish the problem is figure out what is the volume of that one slice, and it will involve x because it will depend on where you took the slice. So the point up here, remember, is just this, and the point down here is just this. So I know the total distance of this black thing is just the difference in the y-coordinates over here. So that minus that. So I have 15 minus x. All right, so now I have some geometry to think about. I have a semicircle where I know the diameter. That's the situation I'm in. I have a semicircle. Let me write this bigger. I have a semicircle, and I know that the diameter, hang on, turn my tablet sideways. The diameter is 15 minus x. Can't even make it x. That's, anyway, diameter is 15 minus x. And what I need, good Lord, and what I need to know is what is the area of that green bit. So the area of the green times delta x will be the volume of that piece. But it's kind of just a weird thing because I'm in a situation where I have a semicircle, and instead of the radius, I'm told the diameter. So that's kind of the situation I'm in geometry-wise. So probably the easiest thing to do is to think about what that geometry formula would be, and then use that in the. Would it be easier? I don't know if it's easier. This is what I need to do. I need to figure this out. So let's see how I would do that. Well, if the diameter is d, and I'm just working with that, so I don't have to deal with the x's yet, but I'll come back to that. So if the diameter is d, then that means the distance from the middle to the edge is d over 2, right, halfway. Why do I care about that? Well, because the area of a semicircle is 1/2 pi times the radius squared. The reason that it's a half is because it's a semicircle. It's half of a circle. A full circle would be pi r squared, so half a circle would be a half pi r squared. But the r, the radius here, is the diameter over 2. So in terms of the diameter, if I multiply this out, in terms of the diameter, the area of the semicircle is 1/2 pi times the diameter squared. So that's what's happening over here in geometry land. It has nothing to do with my picture, but it gives me the area formula for the green stuff in my picture. So the volume of this slice is approximately, I'll say approximately, the area of the green, which is 1/8 pi times the diameter, which is 15 minus x, that's my labeling, squared, times delta x. So that's the volume of a semicircle that has diameter 15 minus x. So therefore, the sum of those is the estimate of the total volume, and in the limit, that becomes the integral of 1/8 pi 15 minus x squared, and the delta x becomes dx. And then the limits of integration are just the possible values of x in the picture, which are pretty clearly 0 to 15. So this is the integral that will answer the question. If you wanted to actually do this integral, which I think is the second part, one easy thing to do would be u substitution. You could do u equals 15 minus x, and this would just become u squared, which is a much easier integral. If you do not want to do u substitution, you could just multiply this out, right? That's just 15 minus x times 15 minus x, and you would just get a polynomial and not have to do any kind of substitution. So either way, this is not a hard integral.